Konnichiwa minasan, welcome back to Business Mathematics. In this video, we will learn about derivative. First, we want to know why we learn differentiation. Well, we say derivative at first, but differentiation and derivatives, they are the same thing but different. I don't know if we will delve into the difference between them, but let's see. So yes, this is the reason why we learn differentiation. Okay, are you done reading? Okay, so let's move on to the next slide. Let's say we have an object dropped from a great height, and this object will fall at the rate of 16 t square feet in t seconds. So we want to know what is the instantaneous velocity after t is 2 seconds. So the average rate of change of st over this time period is something like that, so 64 plus 16h. Now, if the interval gets smaller and smaller, this means h gets smaller and smaller, we will get that after 2 seconds, the object is traveling at the rate of 64 feet per second. Let's change the s from the previous example to any f, any function. How do we determine the instantaneous rate of change of f(x) at x equals to c? We do it in the same way we did in the example. So we start from the average rate, and then we make the intervals to be smaller and smaller by using limit. Then we have the instantaneous rate of change formula for fx at x equals c is this one in limit form. Let us be specific. So let's say if f, or in this case y, is a linear function, so we have the equation is mx plus b, then the rate of change is the change in y over the change in x, or y2 minus y1 over x2 minus x1, which is its gradient, or the slope, or the steepness, or whatever else you call it. While in a non-linear function, the rate of change is not constant, but will be varies with x. So at any given point, CFC, we can see that the rate of change at C is the slope of its tangent line. Let's say we have a function f and x plus h. The second line is the line formed by joining x fx and x plus h, fx plus h. If we make h smaller and smaller, which means h tends to 0, then the second line will also tend toward the tangent line. And so at long last we arrive to the formal definition of the derivative, which is limit h to 0 fx plus h minus fx over h, and it usually noted as f prime x. Here's a little example. So we want to find the derivative of the function fx equals to 2x squared minus 16x plus 35. By using the definition, we will get something like that. And then we have fx plus h minus fx over h is 4x plus 2h minus 16. If we apply the limit of h to 0, then we will get the derivative of 2x squared minus 16x plus 35 is 4x minus 16. From a few slides ago, we already know that instantaneous rate of change is the slope of a tangent line. Here, we will also get that the slope of a tangent line is the derivative. Here's an example to illustrate it. So let's say we have y is equals to the square root of x, and we want to know the equation of the tangent line when x equals to 4. First, we find the derivative of square root of x. So we have f prime x is, yes, by using the definition is something like that, and yada yada yada, something or other. Then we have the f prime x is 1 over twice the square root of x. So the slope of the tangent line, if we have x equals to 4, then f prime 4 equals to quarter. Then we apply that to the point slope form. Then the equation is y equals to x over 4 plus 1. Let's go to the more grounded example. So let's say we have a manufacturer that already have the profit equation, which is something like that. So px equals to minus 400x squared plus 6800x minus $12,000 per x thousand units produced. So when 9,000 units are produced, we want to know what is the change rate in the profit. So we have to find p prime x, which is something like that, by using the definition of derivative. So we have p prime x is minus 800x plus 6800. Now just substitute 9 to the x, so we will get p prime 9 is minus 400. This means that the tangent line to the profit curve is sloped downward at point Q, where x equals to 9. The profit must be decreasing when 9,000 units are being produced. The previous example gives us a case when derivative is negative, then the function is decreasing. This is the general case for any function. So if we have f prime is positive, then f is increasing. And if f prime is negative, then f is decreasing. And here are a few ways to write derivative. So we have f prime, y prime, and we also have df dx, dy dx. This is called the Leibniz notation. Leibniz is the true inventor of calculus. I dare you to change my mind on that. And for the final topic in this video, it is the relation between differentiability and continuity. So if we have a function f is differentiable at x equals to c, then it is also continuous at x equals to c. But it is not always true the other way around. For examples, here are 4 functions which is continuous at 0, but they are not differentiable at 0. And that's it for this video. Before we end this, I want to say determine, determine, potato, potatai. It's all the same. See you in the next topic. Now I'm sure I will see you in the next topic.